Hi everyone and welcome back to the channel. In today's video, we'll be going through a fluid mechanics review to prepare for the FE exam. So if you're studying for the FE mechanical or other disciplines exam, this review will be useful to you. You can see below I have the NCES specification specifically for the FE mechanical exam. One thing I'd really like to emphasize here is that fluid mechanics is a large portion of the FE mechanical exam. You can see it's 10 to 15 questions on the exam. It's a great place to focus in your effort and to really master so that you can maximize your chances of passing. In this review, the structure is we're going to cover these various topics mentioned in the specification via example problems. So we're going to be walking through 11 different example problems, and I've kind of categorized it based off of which problems are associated with which topic. I try to get good coverage here so that we can review the really important ideas from fluid mechanics. Some of those important ideas I tried to note down below, but this list really doesn't do it justice. Just to summarize what we're going to cover here, we're going to cover continuity or conservation of mass. We're going to look at conservation of energy via the energy equation. We're going to look at Bernoulli's equation, conservation of momentum and control volume analysis. We're going to look at drag forces, talk about the idea of internal and external flow, look at the Moody chart. We're going to talk about compressible flow, pump performance, Buckingham pi theorem, and more. You can see on the right-hand side here a subset of schematics from those 11 problems that we're going to be working on today, all of which were taken from my prep software, FE Interactive. This review will follow a consistent format where we'll have difficulty and subject tags on the upper left of the problem. You'll see a diagram if it's applicable for that problem, as well as the problem statement stating what the problem is looking for. We'll have answer choices, since on the FE exam, most of your questions are going to be multiple choice. The majority of them are going to be multiple choice. And you'll also see a specification here where I'll highlight what subject the question is trying to review. You can try all of these problems for yourself interactively for free using the first link in the description below. Once you click on that link, it'll take you to a screen like this. And all you'll do to access the fluid mechanics review is you'll go ahead and click on the filter button, click on fluid mechanics, and then click collapse. And you can see all of the questions and try them out for yourself. Okay, let's go ahead and get into the review. In this problem here, we have a piston. The piston has a diameter, let's call that d sub p, equal to 10 centimeters, with a length, L sub p, equal to half a meter. And it slides concentrically inside of a cylinder. And we're given what the inner diameter of that cylinder is. It's 10.1 centimeters. And the piston is sliding at a rate, a speed equal to 1 centimeter per second. The gap is filled with stationary fluid, and a 5 Newton force maintains the motion, so the force is equal to 5 newtons. We're asked for the fluid viscosity here, and if you recall, there's two kinds of viscosity. There is the dynamic viscosity mu, that's the absolute, or the dynamic viscosity mu, and then there's the kinematic viscosity nu, that's equal to mu over rho. Now, the kinematic viscosity is called that way because there's speed inside of its units. The standard unit for the kinematic viscosity is meters squared per second. And you can kind of see there's a speed term of meters per second inside of that kinematic viscosity. So we call it kinematic because it's more focused on speed and not on forces. The dynamic viscosity has a force inside of its unit. The standard unit for the dynamic viscosity is a pressure times time, right? Like a Pascal second. And you can see that inside of the choices here, we have Pascal seconds as one of the units. A Pascal is just a Newton per meter squared times a second. It's a Newton second per meter squared. You can see that Newton, a force, is mentioned inside of the kind of set of units if we look a little bit more closely. So we're really talking about the dynamic viscosity as this force inside of those units. Okay, so, I want to go through this problem with you guys because it's going to help you review the idea of fluid properties, specifically the idea of viscosity here. And the fundamental relationship for viscosity is that the shearing stress, tau, is equal to the dynamic viscosity multiplied by the velocity gradient, du dy. So in this problem, we're looking for that, we're looking for the absolute viscosity here. So we can find that if we knew what the shearing stress is and we knew what the velocity gradient is. So we're going to go through each of those terms. And finally, we're going to go ahead and take that ratio of the shearing stress divided by the velocity gradient. Now, what I'd like to do here is start off with the velocity gradient. And when we think about the velocity gradient, it's just a ratio of speed, that's this du, divided by um, a gap, right, or a height. And usually we think about this in terms of flat plates. If we think about the fluid that's kind of enclosed between this gap right here, you can kind of picture it as the right end of the cylinder as well as the stationary wall here. I kind of drew it a little bit exaggerated. Now, as we pull up on that cylinder, as we pull up on the piston, the right side surface of that piston is going to be moving with a certain speed. And the speed of the right side will be equal to 1 centimeter per second. The entire surface of that piston is going to be moving at 1 centimeter per second, while the wall will have a zero valued speed. So if we kind of draw the velocity gradient here, you can see that it is triangular and it's linear. Now, it must be linear because they didn't give us any other information to tell us that it wasn't, and we wouldn't be able to solve the problem otherwise. And when this velocity gradient, the ratio of the speed divided by this height difference, this gap here, when that's linear, we call the fluid Newtonian. So we have a Newtonian fluid in this problem. If it was nonlinear, we'd have a non-Newtonian fluid. And we'd have to be given extra information to solve the problem at that point. Now, if we fill in what the du dy is, the velocity gradient, we can fill it in over here. The change in the speed over the gap, that's just the entire speed, v, divided by the gap. Now, what is the gap? If we look at the diameter here, this is that diameter of the cylinder, and this one here is the diameter of the piston. Now, if we take the difference between these two and divide it by 2, we'd be able to find what this gap is here. So we're going to take the diameter of the cylinder, subtract off the diameter of the piston, and cut it in half to just get one side of that gap there. Okay, so we were able to find the velocity gradient, and it depended on a really important idea called the no-slip boundary condition. On the right side wall, you could see that we are perfectly stationary, and any fluid that is adjacent to the right side wall is going to have a zero valued speed. It's going to match the speed of the object that's next to it. Same thing for the cylinder, right? There's no slip. Same thing for the piston. There's no slip on that side. So anything that is adjacent to the piston, that will be moving at the same speed as the piston, that 1 centimeter per second. So this is the correct velocity gradient, and we have a way to find it on the right-hand side. What about the shearing stress? As we pull up on that piston, there's going to be some shearing stresses that develop on the piston surface. Shearing stresses are parallel to the surface. So you can kind of picture all of these little stresses that would be acting downward as we're pulling upward. And that's going to be kind of what's balancing it and what would allow it to move with a constant speed. We know what the force is. The force that's pulling up is 5 newtons. And that force per unit area is what we call that shear stress. Force per unit area is shear stress. And remember that those shearing stresses are parallel to the surface. So I kind of visually drew what the shearing stress is here. The shearing stresses are there. It's a force, 5 newtons, divided by the area. Where would the area be that shear stress is acting on? It's the entire kind of surface area around that cylinder. The surface area is just the circumference of the piston, which is pi times d sub p, multiplied by the height, which is just L sub p. So now that we have everything that we need to be able to plug in here, force divided by pi d sub p L sub p. We should be able to find exactly what we need. So let's go ahead and plug in some of these numbers. Just to quickly be consistent with some of these units, I'm going to convert all of the centimeters to meters here. And this one would be 0.01 meter per second. Now I'm ready to plug in. All my units should be consistent. I know what the force is. That force is equal to 5 newtons. I know what d sub p is. That d sub p is 0.1. I know what the length of the piston is. It's 0.5. I'm going to take that entire thing and divide it by my speed. It is 0.01 meter per second divided by the diameter of the cylinder is 0.101 minus 0.1 is the diameter of the piston. I'm going to divide that by 2. I'm going to go ahead and plug this into my calculator. 1.59. And we know that the standard unit here is Pascal seconds. So the answer choice is A. Before we move on to the next problem, I just wanted to go through the FE reference manual with you guys and show you where you can find some of this important information. On the first page here of the FE reference manual in the fluid mechanics section, it's page 177 in the 10.4 version, where we're first discussing some of these properties, density, specific weight, specific gravity. We'll be discussing those in further, kind of in later parts of this review. There is a section on viscosity here, which would be the relevant part for this question. You can see they have Newton's law of viscosity, the definition of shearing stress in here, the absolute and kinematic viscosity that we discussed in this problem, as well as the idea of a Newtonian fluid and how the velocity profile is linear in that case, just the ratio of the speed to the gap. And they even mentioned something about non-Newtonian fluids, and we need this power law index to be able to solve a problem for a non-Newtonian fluid. So we'd be given that, or we can somehow calculate it if we were solving a problem for a non-Newtonian fluid. Now, I'm not going to discuss surface tension and kind of capillary action inside of this review. So if we quickly take a look at it, it's pretty much just plugging into a couple of these formulas over here. Something about the capillary rise they mentioned inside of the reference manual. They have all this kind of relevant information on capillary rise as well as the idea of surface tension. So you can see it's a small section here, but we got to talk a little bit about it in the video. Let's go ahead and move on to the next problem here. In this problem here, we have a fluid system that's shown above, and we're looking for the head difference in centimeters of water column, and we're going to talk about what exactly that is between the two tanks above. You can see that there's a tank on the left, there's a tank on the right, and we're looking for the pressure difference measured in head, right? So an important equation here is the hydrostatic pressure equation, which is that the pressure is equal to density times gravity times height. The product of density times gravity is a term called the specific weight. So we can also write this as the specific weight of that substance times the height. What head means is if we take the ratio of the pressure divided by that specific weight, we get the height. What's shown on the left term is pressure. That's the P. And what's shown on the right side is the head. So if you ever seen a weather forecast and the weather man or woman gives you the pressure in millimeters of mercury, that's kind of similar to the idea of centimeters of water, right? Which is the unit that we're looking for the head here. So if you're given a head in centimeters of water, how you can convert that to a pressure is what it physically means is if you had, let's say, a static column, and that column contained 10 centimeters of mercury or 10 centimeters of water here, the pressure exerted at the bottom of that column would be equal to whatever the gamma of water is multiplied by the height of that column. That's 10 centimeters. So it would be like 10 gamma. And gamma is like, 1,000 kilograms per cubic meter multiplied by gravity. So it's 9810 newtons per cubic meter. Okay, so we talked all about head, and what we're going to do is go ahead and talk about how to solve this problem now. And that really goes back to the idea of this hydrostatic pressure equation. If you're in the same fluid at planes of equal elevation, you will be at the same pressure, right? So those two red dots that I highlighted there, those are going to be at the same pressure because they're both in the mercury fluid and they're at the same elevation. And additionally, if you descend in a static fluid, you're going to be increasing the pressure, and you could find what the pressure is by using the hydrostatic pressure equation. If you ascend, then you're going to be decreasing the pressure. So let's say we start off at the second tank on the right-hand side here. We start off right here. What we can say is that the pressure in the second tank, as we descend to get to this point right here, which is the same pressure as what I highlighted over here, all we would do is add the gamma of mercury multiplied by the height, which is 25. So that's just 25 gamma, and I'd be at this pressure right here. But then I have to ascend in the fluid to reach this first tank here. I'm going to ascend by 31 plus 22 at some angle. And these are vertical heights, right? It's not any diagonal heights here. We want this height right here. That height is 22 times 3 over 5. You can see there's a little slope triangle over here. It's like, if we label this angle right here theta, then we can say that the sine of theta is equal to 3/5. 22 times the sine of theta is what we're looking for, 22 times 3/5. Okay, so this comes out to be 44.2 centimeters. So we're starting off at this point right here, and as we ascend in that fluid, we're going to subtract off the gamma of water multiplied by 44.2. And at that point, we'd be at the pressure of the first tank. So this is our equation right here. And, they didn't give us what the specific weight of mercury is, but they did give us what the specific gravity is. And specific gravity, the definition of it, it's just the density of any substance divided by the density of water, or the specific weight of any substance divided by the specific weight of water. And that makes sense, right? The only difference between these two terms is gravity, so they would cross out on the top and bottom. But if we divide out our equation by the density of water, divide this by gamma on this side, we're dividing our entire equation by gamma here, and just let's move the P2 to the other side. What we'd have is P1 minus P2 divided by gamma, which looks like a head term. That is going to be equal to this ratio over here is the specific gravity of mercury, which is 13.6. You can see it's given in the diagram right here. 13.6 multiplied by 25, that's the height, minus, and what is the specific gravity of water? It's going to be equal to 1, right? You take this and divide it by itself. You're going to get 1, so that's subtract by 44.2. So our solution here is going to be 13.6 times 25 minus that 44.2 to get 295.8, and everything was measured in centimeters here. And technically, we're talking about centimeters of water since we normalized to water here. And you can see that that's pretty close to this answer choice C. I guess you can't see it on the screen here. So it would be answer choice C here. All right, let's go ahead and check inside of the reference manual, page 179, where we could find some of this information. Okay, on page 179 here, you could see that they mentioned some things about manometers here. And on 178, they're mentioning some things about static liquids, right? And they have the equation of hydrostatics here. They use a negative sign, and I usually assign that sign based off of whether we're ascending or descending inside of a static fluid. But fundamentally, pressure is just the specific weight times the height. And you could see that they talk about manometers and how to develop that equation, which we understand how to develop. There's also mention of a barometer, which we spoke a little bit about, right? And that's pretty much it for this problem. Let's go ahead and move on to the next one. In this problem here, we have a green rectangular gate with a depth of 2 meters. So that's the depth into the page. D is 2 meters. It's submerged in a body of water. So we know that the fluid here is water. And it's shown above. The gate is pin connected at its upper edge and it's in smooth contact with the ground. At its lower edge, the reaction force exerted by the ground on the gate is most nearly. So if we kind of quickly drew a little free body diagram here, we separated this body and kind of drew the reactions here. We'd have pin reactions at that upper edge where it's pin connected. There'll be a normal force exerted from the ground onto the gate. And then additionally, there'll be some pressure force, right? And I'm drawing that as a point load. It would technically be a distributed load placed at a certain point. That point we call the center of pressure. And the entire problem basically boils down to finding that resultant force and where to place it. We can take a moment at that pin and then find what the normal force is. And, we can plug into those massive set of equations, but I'm going to show you guys a method that really depends on your understanding of statics and feels much more intuitive to me. Before we go ahead and do that, I'm going to show you guys in the reference manual this section on submerged surfaces. It's on page 180 here, and the idea of center of pressure. They draw this schematic and they give you a massive set of nomenclature here, and you have to find moment of inertias and center centroids and center of pressures. And I think these equations are super complicated and unnecessary for the problems that we'll get on the FE exam. You can just draw that pressure distribution, find the centroid, and place the resultant force at the centroid of that pressure distribution. And this volume under the pressure distribution is going to be equal to the magnitude of the resultant force. And this is called the pressure prism method. It's the method that we're going to be using to solve this problem. It's much more intuitive, and I think it's a lot faster. And the entire kind of method breaks down to being able to draw that pressure distribution correctly and understanding the equation of hydrostatics. So before we get into that problem, I'm going to go through a couple of different examples with you guys on how we draw that pressure distribution, because that's the most important part. Just like we saw for the manometer problem, the equation of hydrostatics is pressure is gamma times H. And we're going to look into that gamma term a little bit more, right? Gamma has units of newtons per cubic meter and can be interpreted as a weight per unit volume, or it could be interpreted as pressure per unit depth. And that's how we're going to interpret it in this problem here. If we put a coordinate system on the top of our surface here, like we had a height here, we had a height H here, and a pressure P here. As you increase your depth in a static fluid, you're going to increase the pressure. You start off at 0 at the free surface and you descend in that static fluid. You'd reach some pressure equal to gamma times your height. The slope of this line, the amount of pressure increase per unit depth, is gamma over 1 here. And that's really what gamma represents. You can see that we were able to successfully draw the pressure distribution here. Pressure is fundamentally force per unit area. Or if we wanted to rewrite this, we can write the force is equal to pressure times area. And if we had a pressure distribution which was changed, we could do is find the resultant force by integrating the pressure with respect to the differential area. That means that if we had some kind of pressure distribution here and we wanted to find what the resultant was, we can go up to that pressure and take a little differential area and raise it up. If you do that for the entire volume, what you get is a total volume under that distribution. So here we'd find the volume of this triangular prism here, and we'd be able to find what the total force is, and we place it at a third of the distribution, right? That's because the centroid of a triangle is a third of the way, and it would be kind of here, 1/3 here from the bottom surface. Now, what if we drew the pressure distribution for this one, which has some depth already? Well, it would be at some pressure here, and it would be at a greater pressure here. We can find what both of those pressures are. It's just gamma times whatever height those ends are. And you can see that the pressure always acts perpendicularly on the gate. So this would be the pressure distribution here. You could split this up into a rectangle and a triangle. Place the volume of that rectangle at the centroid of that distribution. So there'd be one right here. This is due to that rectangle, and then there'll be one at a third of the way down due to that triangle. Right? So you would have two forces there. How would we draw this pressure distribution here? We have 0 here, and we'd have some pressure here at the lower surface. And note that we always have a perpendicular line to our pressure distribution here. So that's how you would treat it for an inclined surface. Same thing right here. Again, we have a trapezoid. It's perpendicularly placed. So you guys kind of get the idea here of how to draw these pressure distributions. What about for a curved surface? Same exact idea, except we take out the free body as this entire chunk of water. There'll be a pressure exerted here on this end, like this. There'll be a weight due to this chunk of fluid that we took out. And there'll be a pressure exerted at the bottom, which will be constant because we're at the same depth. Constant pressure here on the bottom. And we can go ahead and put those resultant forces. There'll be one resultant force at a third of the way here, and then one in the center. So we understand how to draw that pressure distribution. We had a lot of opportunities here to go ahead and draw that pressure distribution. How do we use that information to solve this problem? Just like we did before, we're going to go ahead and start off with drawing that pressure distribution here. We're going to draw in red for clarity. We'd have, of course, two pin forces here, a normal force on that bottom surface. And if we draw the pressure distribution, we know that's this height right here. This is 5 times gamma. That's the pressure at this point. What about this one? This pressure is 8 times gamma. We could connect those points here, and we get this pressure distribution, or this prism, a trapezoidal prism that we can split up. We can split it up into a triangle and a rectangle here. Remember that if we find the volume under that distribution, we're finding the total force. Now, what is the force due to that rectangular contribution? If we think about the volume of that distribution, it has a height, which is right here. Height is 5 gamma. The length of the gate, let's call it L. So we just found the area right here. And we have to multiply through by the depth. And what was the depth? It was 2 meters. The depth is 2 meters in this case. So I would multiply through by that depth. That is the rectangular contribution that we would place right there at the centroid. Centroid of a rectangle. Let me draw it in a different color here, so it's a little bit more clear. We would place it right here at a distance is L over 2, half the length of the gates, and its magnitude is 5 gamma multiplied by LD. What about for the triangular contribution? The triangular contribution here will have a height of 3 gamma. It has a length equal to L, and we divide that by 2. That is this area right here. And of course, we multiply through by the depth to get the volume. This is the resultant force due to that triangle. So if we go ahead and draw that right here, we have what this is. It's 3 gamma over 2 multiplied by LD. Okay, so that is what the contribution is due to that triangular portion. I'm going to clean this up a little bit so that we're able to more clearly see what we're looking at on the free body. Okay, so now that I cleaned it up, I placed those distances here. You can see that I placed that rectangular contribution at L over 2, and I placed the triangular contribution at 2/3 of the length down. All we do is take the moment about the pin. Let's call that pinpoint P. If we go ahead and sum the moments about that pinpoint P and set it equal to 0, we'd be able to find what that normal force is. We'll say counterclockwise is positive, and the only counterclockwise contribution here is that normal force contribution. So we have N multiplied by our distance. Kind of this, we think about what the moment arm here is. This would be our line of action of the normal force. We're looking for just the horizontal distance, the perpendicular distance from P to that normal force. If we call this length right here L, we had that similar triangle, that 3, 4, 5 right triangle, 3, 4, 5 right triangle. What you could see is that the height right here is 3, right? It's the difference between 5 and 8. That means that the length of the gate is 5. Instead of writing in terms of numbers, I'm going to say it is L, and I'm going to call this theta here. We know that the kind of horizontal distance would be L cosine theta, and the cosine of theta is just 4/5. So I'm going to call that distance 4/5 of the length. And that counterclockwise distribution must be equal to the contribution here due to all the clockwise moments. There's one due to that rectangular resultant force, 5 gamma LD, multiplied by the distance. That distance is half of the length. And then we also have another contribution due to that triangle, 3 gamma over 2 LD, multiplied by 2/3 of the length there. You could see that all of the lengths cross out here. Additionally, this 3 will cancel out. This 2 cancels out. We have a simplified expression here, which says that the normal force is 5/4 5 gamma L D. Still have a divide by 2 here, plus gamma LD. So we have 7 over 2 gamma LD, and we multiply this by 5/4, and that would be our final answer here. What is the length of the gate? The length of the gate that we saw over here is 5. So we plug in 5 right here. The depth we saw before, the depth was given in the problem. That is 2 meters. That's the width into the page. We have 43.75 times gamma. Gamma of water is just the product of density times gravity. The density of water is something that you should memorize for the FE exam. It's 1,000 kilograms per cubic meter, and gravity is 9.81 meters per second squared. So this turns out to be 9810 newtons per cubic meter. We plug this in right here. What we find is that 9810 times that 43.75. This is measured in meters. Will be measured in cubic meters here. Everything is measured in meters, so I know that all the meters are going to cancel out. We're going to be left with newtons. It's 429,000 newtons, or 429 kilonewtons. So that is answer choice D here. You guys can see this. Let's go ahead and move on to the next problem. In this problem here, you could see we have another question related to the topic of fluid statics here. And specifically, we'll be talking about buoyancy in this problem. So let's get right into it. It says an ice cube with a height of 4 centimeters floats upright in a glass of water. If 3 millimeters of the cube is above the water surface, determine the density of ice. Okay, so let's transfer this to a clean sheet of paper. Now, a lot of people never really thought about it, right? Ice is actually less dense than water. That's why we have glaciers floating on top of water. And it has something to do with hydrogen bonds, but let's not get off topic here. It says, firstly, an ice cube with a side length. The ice cube side length is 4 centimeters. It's a cube, so all the side lengths, including the depth, are 4 centimeters. They said that ice cube is floating in a glass of water in 3 millimeters of the cube. Now, what we know is that 3 millimeters is the same thing as 0.3 centimeters. So if we kind of draw it out here, that would mean that this kind of height above the surface, this is that 0.3 centimeters. That would mean that this would have to be 4 minus 0.3, which is just equal to 3.7 centimeters. Okay. Now what we need to do is determine the density of the ice. Now, usually when we have a body floating in water, any kind of object, we have to think about Archimedes' principle. And Archimedes' principle is related to buoyancy. Objects float because they have a buoyant force. And basically what happens is there's the weight of the object, which points down. Additionally, there is the buoyancy force, which is pointing up. And when these forces balance, we have a static equilibrium. Think of static equilibrium. What's the equation for that? We can write the sum of the forces in a particular direction, let's say the vertical y direction, must be equal to 0. What that's telling me is that the buoyancy force is equal to the weight. Now, we know how to compute the weight, right? The weight is just, we can take the density of that object times gravity. Density times gravity is defined as the specific weight. So in order to compute the weight of that ice cube, what we could do is we could take gamma of ice and multiply it by the volume of ice. If you recall, gamma's units are newtons per cubic meter. If we multiply it by a cubic meter, what we would get is the weight. Just to kind of review what that gamma is so that it's not confusing. What we could do is go into the fluid mechanics section, go up to the top near definitions. It'll tell you exactly what gamma is. Gamma is just called the specific weight, and its units are newtons per cubic meter. It represents a weight per unit volume. So if you multiply by the volume, you'll get the weight of the object. Okay, so we understand what gamma is. Additionally, other things are going to come into this problem, like the specific gravity, which is just a ratio of densities or a ratio of specific weights, which are exactly the same. Right? Remember, specific weight is density times gravity. The gravities will cancel out on top and bottom. You can see the definition here. So specific gravity is always relative to water. Something with a specific gravity greater than 1 would be more dense than water. Less than 1 is less dense than water. Okay, so we understood some of those definitions here about the specific weight, and we found the weight of the water. We found the weight of the ice. What about the buoyancy force? Where the buoyancy force comes in is that Archimedes' principle basically states that the buoyancy force is equal to the weight of the displaced fluid. Now, it's kind of confusing to say it like that, but in our case, if we focus in, the ice is sunken into the water and it displaces a certain amount of fluid. You could see I'm shading in that ice cube. That volume of the fluid has been displaced. What is the fluid that's been displaced? It's water. So we're talking about the specific weight of water multiplied by the volume that was displaced. Well, that's almost equal to the volume of the ice, except this base term is the same, the depth term is the same, but the height is now 3.7, right? So we have that volume of the displaced fluid. Let's see if we can fill in some of these terms. Gamma of ice divided by gamma of water, that's just equal to the specific gravity of ice from those definitions that we were referring to before. Once we have the specific gravity of ice, what we know is that that's equal to the volume of the displaced fluid divided by the volume of that ice cube. Now again, thinking about the volume of the displaced fluid, what we have is that it's equal to 4 squared. That's this base times the depth times the height, that is this 3.7 centimeters here. And we have the volume of the ice cube. The volume of a cube is just the side length cube, that's 4 cubed. What we can see is that it's just a ratio of 3.7 over 4. The ratio of 3.7 over 4 is equal to 0.925. That's equal to the specific gravity of ice. Now, knowing the specific gravity that we have of ice, it makes sense that it's less than 1 because this object is floating, it's less dense, so that means it would want to float. We also know that the specific gravity represents a ratio of specific weights, or alternatively, it could represent a ratio of densities, like the density of ice divided by the density of water. The density of water is 1,000 kilograms per cubic meter. If you watched a few of those other videos, you know that that's a number that really comes up a lot, so I recommend you go ahead and memorize that value. We can find the density of the ice by just doing that 0.925 and multiplying by the density of water, which is just 1,000 kilograms per cubic meter. That means that the density of the ice is 925 kilograms per cubic meter. Let's go ahead and check that answer here. We have the 925 and we got the solution correct. Additionally, if you didn't remember Archimedes' principle, we can go ahead and check inside of the reference manual. You can see Archimedes' principle here. The buoyancy force is equal to the weight of the displaced fluid. Let's go ahead and get into the next problem. In this problem here, we're going to be working through a Bernoulli's equation example. You can see I have highlighted the energy equation. I'll talk a little bit about the differences between the two when we're solving the problem. Let's get right into it. It says, the figure above shows water flowing vertically upward through a tapered pipe. The diameter at the lower section of the pipe is 50% larger compared to the upper section. A fluid with a specific gravity of 2, along with water, are used in a manometer connected to the two pipe sections. We're looking for the volumetric flow rate in the pipe. Let's transfer this to a clean sheet of paper here. And let's note down some of our givens. Firstly, it says that the water is flowing vertically upward through a tapered pipe. And additionally, what we have is that the lower section of the pipe is 50% larger. That means that if the upper section of the pipe is D, the bottom section of the pipe would be 1.5 times D, or 50% larger. Additionally, it mentions like some stuff about specific gravity here. If we quickly think about what a specific gravity is, a specific gravity represents a ratio of two densities, a density of some substance related to water. Additionally, it could represent the product of density times gravity in relation to water's density times gravity. Density times gravity is the specific weight. So it represents a ratio of densities or a ratio of specific weights. And that's called the specific gravity. And it's mentioned because this fluid here in this manometer has a specific gravity of 2. So we're going to be needing to use that. It's asking in this problem for the volumetric flow rate, Q, like it's mentioned in the manual. And Q is just the product of the area times the speed, where A is the cross-sectional area and V is the speed at that section of the pipe. Now that we've compiled all the given informations, we can think about what formula we would use to solve a problem like this. We're looking for a flow rate, and you can see from this formula here, flow rates are related to speeds. We're given some information about pressures indirectly because we have these manometers here. These manometers represent static fluid, and as we increase depth into a static fluid, what we have is an increase in pressure. That increase in pressure is just gamma, the specific weight, multiplied by the height that we kind of descended into the fluid. So we know some things about pressure, and we're essentially looking for some things about speed. And there's a relationship between pressures and speed, and that is in the Bernoulli's equation. There's also mention of it in the energy equation. Now, when do we know to use Bernoulli's or the energy equation is if we're given some information about losses, or we have a pump or a turbine inside of our problem, we'd use the energy equation. We don't have any of those things here, so we're going to use Bernoulli's equation. Now, if you go here in the reference manual, this is on page 181 of the reference manual, you can see some information about continuity or the conservation of mass. That's going to be important for us because we have a single flow and we kind of have a constriction. But we know that the mass flow rate, or in this case, since we have an incompressible fluid, the density is the same at point 1 and point 2. What we know is that the flow rate has to be the same in the pipe. It's only one flow. So that's going to be important for us. Additionally, we have some information on Bernoulli's equation. And I like this kind of upper form of Bernoulli's equation, which is head form. The head form only has terms written in with units of meters or combinations of terms. So it's pretty simple in terms of what kind of units you get out of it. That's why I like it. And there's another form shown below. We're going to be working with the head form here. If we go ahead and write down Bernoulli's equation, one of the first things that we're going to have to do in Bernoulli's equation is identify 2 points of interest. Now, where are we going to place our points of interest? The first points that pop out to me are the ones that are connected to the manometers. I would label this point as 2 and this point as 1. And I labeled it in this order because the flow is flowing upward from point 1 to point 2. I picked these 2 points because using the idea of manometry, we can easily find pressures at these points. Points at the same depth in the same fluid have the same pressure. So that's why I chose these points, because they're connected to those manometers that we could find the pressure of. We understand what our point 1 and point 2 is. Now, if we're able to isolate the speed, we can algebraically manipulate it to bring into the problem what we're looking for, which is the flow rate in the pipe. So let's go ahead and do that. The first thing that we're going to do is, again, isolate those speed terms. We have a difference of speeds on the left-hand side, and essentially we have some other terms on the right-hand side. We moved over that 2g term, and we have a difference of pressures on the left-hand side. P1 minus P2 over gamma, plus the difference between Z1 and Z2. And this would be what we have on the right-hand side. Now we have a difference of 2 speed terms. If I multiply this left-hand side term by A2 over A2 squared, and this term by A1 over A1 squared, what I end up getting is I'm able to see that the flow rate comes into the problem. Like for instance, for this term, I have an A2 times a V2 squared. That's just a Q value, or volumetric flow rate squared. And if I kind of extract that out, what I have is a 1 over A2 squared term here and a 1 over A1 squared term here. I'm going to go ahead and set that equal to the right-hand side term. Now that I have that right-hand side term, I can move over these kind of set of areas here. And what I'm left with is just that Q term. And it's that term squared. So I can take the square root later, but let's try to find some of these terms. We mentioned some stuff about the manometers and how they could be used to find the pressure. What I know is that the pressure of 1 is given by rho GH, where my density, I have 2 different fluids here, right? If I start at this upper surface, which has a gauge pressure of 0, I descend inside of the fluid until I reach this second point where the fluid is going to change. The pressure at that point is equal to the density of that fluid. It's twice as dense as water multiplied by the depth that we went into that fluid. So the pressure right there is 4 gamma. I'm going to descend by 3 more gamma to end up at this point, which is equal to the pressure at point 1 since they're at the same elevation. That's equal to 4 plus 3 is 7 gamma. And what about the pressure at point 2? The pressure at point 2 is just going to be 2 gamma. We're just looking at water there. Additionally, we did have some elevation terms here. The difference between Z1 and Z2. If we make our datum here, that means that the elevation at point 1 is just going to be 0. The elevation at point 2 is 3 meters higher. So if I go ahead and make some of those substitutions here, what I get is that the Q squared term is 2G. Remember that P1 term was equal to 7 gamma. The P2 term was equal to 2 gamma. And we have a gamma in the denominator here, which cancels out. We'd end up with just a 5 here, and then subtract off the elevation difference. Remember that was 3 meters. And it's subtract because this is this minus sign right here. We have a 5 minus 3 term. That ends up being a 2. And then what I like to do for the denominator is I like to write it in terms of non-dimensional kind of ratios. So if we factor out a 1 over a2 term in the denominator, what I get is a 1 minus an a2 over a1 squared term right here. What is a2 over a1 squared? Remember that a2 was just pi d squared over 4. And A1, it had a 50% larger diameter. So it would kind of be like pi times 1.5d squared over 4. Some of these pi's and 4's cancel out. So essentially, a ratio of areas, A2 to A1, is equal to a ratio of diameters, which both cancel out, and I get a 1 over 1.5 squared. Now that's a ratio of areas. I'm going to again square it when I stick it back in there because that just represents the single ratio of areas, but I want that term squared. So I have a 1 minus 1 over 1.5 essentially raised to the 4th power inside. A 1 over a2 term squared. Remember a2 is just pi d squared over 4. If I take its reciprocal, I'll get 4 over pi d2 squared, where d2 or d, that was just equal to 45 centimeters. Remember, I'm going to square this whole term. So I have that in the denominator as well as the numerator. That's this 2 here times 2g. I get 4g in the numerator. Okay, so now if we go ahead and plug in and compute some of these values, we know that g was just equal to 9.81. So I'll plug in, take the square root, and let's also make sure we check out some of these units, right? What are the units of the numerator here? The numerator just has units of meters. That's from this. The 5 minus 3 was just a meter term. What about the gravity? That's measured in meter per second squared. So the numerator has units of meter squared per second squared. The denominator has units of 1 over centimeter to the 4th. Now, what I recall from previous kind of looking at the question was that it was measured in liters per second was those final answers. I know that there's 1,000 cubic centimeters in a liter. Now what I can do here is I'm going to convert everything to centimeters since there's a relationship between centimeters and liters. And in a meter, there is 100 centimeters. I have to square this here. So that all my units work out, I end up with a centimeter to the 6th, 10 to the 4th, centimeter to the 6th over second squared. We're going to go ahead and plug all of that in. So our Q term is just equal to 4 times 9.81 multiplied by 10 to the 4th. We're going to divide that by 4 over 45 squared pi. We're going to square this entire thing and multiply by 1 minus 1 over 1.5 raised to the 4th. What I end up getting here is that's measured in cubic centimeters per second. Remember, I went ahead and took that square root as well. And we know that there is 1,000 cubic centimeters contained in a liter. So if we divide that answer by 1,000, what we end up getting is Q is equal to around 11, 12 liters per second. So that's what Q is equal to. Let's go ahead and check that solution. It's pretty close to this answer here. Let's go ahead and move into the next problem. In this problem here, we're going to be going over the energy equation and the idea of internal flow. which is really just when flow is flowing through a closed cross-section like a tube or a pipe, as opposed to external flow, which is when we have flow over a body or in an open channel. Let's go ahead and get into the problem. So it says the volumetric flow rate, water is flowing at 1.75 cubic feet per second. Volumetric flow rate because it's cubic feet per second, a volume per unit of time. We're given a diameter here of 5 inches. Now water is flowing through that pipe. That pipe length is 160 feet long. And it's connecting two large tanks as shown. The pipe, it has a roughness value of 0.002 inch and a kinematic viscosity value of 1.08 times 10 to the negative 5 feet squared per second. It says neglecting minor losses, the elevation difference, h. What is that h value equal to? Okay, a lot of things in this problem. We're given a few different givens. First thing is that we are looking for that height h. If I'm thinking about what kind of equation can I use to bring into the problem the elevation, I'm also noticing that we're given this E value, a roughness value for the pipe that's associated with friction losses. So I'm thinking that we need to use the energy equation. And what the energy equation says is that basically this equation here, P1 over gamma plus V1 squared over 2G plus Z1. The energy equation is almost exactly the same thing as Bernoulli's equation, but there's an additional term here, the head loss due to friction. Now, the head loss due to friction can be broken up into two terms. There's a major loss term, and there's also a minor loss term. The minor loss term are due to pipe bends, elbows, entrance effects, like what we have here when we're flowing into this reservoir. What the problem says is that we want to neglect those minor losses. So we don't have any minor losses, but we do have a major loss. The major loss is associated with friction losses due to a straight length of pipe. Okay, so it looks like we have this. And if we want to see where we got this in the manual, we can go ahead and do that. Okay, so we see the energy equation here. That's this. This is head form, so all of these terms have units of length. And this is pretty simple. I like this kind of form of the energy equation. We're going to make some simplifications later, but you see we have a friction loss term and we also have an elevation term, so it's going to bring into the problem that h value that we're looking for. So we have that. Also, we know that the volumetric flow rate is the area times the speed. That's going to come in a little bit later. And you see Bernoulli's equation on the bottom. So that's where we got the energy equation information. This head loss due to friction, the major loss, it can be found using this Darcy-Weisbach equation. So that's what we're going to do in this video. What we need is the friction factor, the L over D, and the V squared over 2G value. The friction factor is found using the Moody diagram. And the Moody diagram relates as a dimensionless chart that relates the Reynolds number relative roughness to this friction factor. So we're going to end up using that Moody diagram, and it's at the end of the fluid mechanics section, which is this. You can see on the x-axis we have the Reynolds number. We have a relative roughness value. That's a dimensionless term. It's that roughness that we're given divided by the diameter. We kind of go up knowing the Reynolds number to a certain relative roughness value and move over to the left to get that friction factor value. So that's our general plan for this problem. Let's see if we can make some simplifications here. Firstly, we need 2 points to be able to use the energy equation. Let's say point 1 is the top and point 2 is the bottom. And I made it this way because this is the way that the flow is going to occur. There's no pump in the system. So that means we're not going to be going from the low reservoir to the high reservoir, but naturally we want to flow from that high point to the low point. Okay, because we have a large reservoir, what that means is that the surface height is not going to change much. That's because it's so large that the tank is going to drain very slowly. That means these points on the surface, point 1 and point 2, will have negligible speeds. And this is a pretty classical assumption when it comes to these reservoir problems. And if you don't get a problem like this on your FE exam, you'll most likely get a reservoir problem, maybe not on the energy equation, but maybe Bernoulli's equation. So these kind of assumptions are important to know. So make sure you understand that point 1 and point 2 have a zero value speed. They're draining very slowly. Their pressures are also atmospheric or zero gauge. So all of these terms are going to be zero. Those 2 points on the surface are exposed to the free air, right? So they have atmospheric pressure. Atmospheric pressure is the same thing as zero gauge pressure. We also have these elevation terms. If we make our datum aligned with that point 2, the lower point, we can kind of get rid of this Z2 value. And what we get is the Z1 value is just equal to the height H. That height H is equal to that head loss due to friction, the major loss. That's just equal to F L over D, V squared over 2G. We said that we can get this F term here using the Moody diagram, but we have to know the Reynolds number as well as the relative roughness. So let's go ahead and make those calculations now. The Reynolds number is just the speed times the diameter divided by the kinematic viscosity. It's a dimensionless term. So you see here, we're not given the speed, but we are given the flow rate. We know that the flow rate is just equal to the speed times the area, or we could solve for the speed doing the flow rate divided by the area. Now, I hate solving for things that I don't need, and you don't really have time to on the FE exam. So I usually try to use algebra to use my givens without calculating anything I don't need. I don't need that speed term, so I'm not going to calculate it. If I replace the area here, which is pi d squared over 4, what I get is 4q divided by pi d squared. So I'm going to substitute that into the Reynolds number. I have a diameter term that's going to cancel out with one of the d's on the speed term. What I get is 4q divided by pi d nu. If I go ahead and plug in what I'm given, I know the volumetric flow rate is measured in cubic feet per second. There's a pi term. The diameter is measured in inches. I'm going to convert that to feet by dividing by 12. And then my kinematic viscosity, that's also measured in feet and time, so those will cancel out the units. 1.08 times 10 to the minus 5. If I go ahead and plug this in, let's see what I'm going to get. My Reynolds number is equal to 4.95 times 10 to the 5th. I usually write it like this because on the Moody diagram, we have powers of 10. There's a log scale on the bottom. So you want to have that times 10 to the 5th or 10 to the 6th or whatever you have. You want to write this in scientific notation. It makes the diagram easier to read. The next thing we need is that relative roughness value, the E over D. The roughness was given as 0.002 inch, and the diameter was 5. What that turns out to be is 0.0004. Lots of zeros there. Okay, so the next thing that we're going to do is knowing the Reynolds number and the relative roughness. We're going to go to our Moody diagram in the FE exam manual. Now 4.95 times 10 to the 5th, that's approximately 5. So it's where my mouse is, right? Between 10 to the 5th and 10 to the 6th, we have this 5 times 10 to the 5th term. We're going to go up until we reach this value, 0.0004. Now that's this point right here, and we'll just travel straight to the left. So it looks like we're around here. Each of these little lines here looks like 2, so this is 10, 12, 14, 16, 18, 20. We're right around here between 16 and 18. I'll call it 17. So our friction factor is F 0.017. Okay, now we're ready to go ahead and plug in all our numbers. Remember that speed term was just 4q over pi d squared. if we just write down quickly what the speed squared term is, that's 16q squared divided by pi squared d to the fourth. Now what I'm going to do is plug in everything here. I have f L over d. I have a 2g term in the denominator, and I also have that v squared term. That's 16q squared divided by pi squared d to the fourth. I'm going to go ahead and make some simplifications here. We have f, L, we have a 16 and a 2 here. That's going to cancel out to make an 8. We have a d to the fifth. Here's an 8q squared divided by pi squared. There's a d to the fifth and a gravity term. Let's make sure this is correct. 8f L, there's a q squared in the numerator, d to the fifth in the denominator, pi squared and g. Okay. Now that we have all of this, let's go ahead and plug in. We have that f. We found that from the Moody diagram, 0.017. The length was 160 feet. Multiply that by 8, and we know our flow rate was 1.75 squared. We have a pi squared in the denominator, a 5 to the fifth, as well as a gravity term. Now this was an English units problem, so our gravity is 32.2. Let's work out all the units. Okay, so the 160 was measured in feet. The 1.75 was measured in cubic feet per second, but that's squared, so it's feet to the 6 over second squared. We have an inches to the fifth in the denominator and a feet per second squared. We know that there is 12 inches in a foot, and that's raised to the fifth power. How do the units work out? We have all the feet end up canceling out, the feet to the 6. There's a second squared, and the inches are gone. We're just left with feet, which makes sense. We're looking for height in feet. Let's go ahead and calculate this out. We have that 12 to the fifth in the numerator, so make sure you include that in your calculation. And we end up getting approximately 16.7 feet. Let's go ahead and move on to the next problem. In this problem here, we're going to be discussing the idea of the momentum equation for a control volume, and we're going to go through the common pain points like how to get those signs correct and how to write down that vector equation and isolate different components. Let's get right into it. So it says, for the constant diameter 12 centimeter water system shown above, the required horizontal anchoring force is most nearly. Okay, let's transfer this to a clean sheet of paper, and let's write down some of the things that we're given here. So the diameter of this system is 12 centimeters. That's this. And it also says a water system. The density of water in the metric system is 1,000 kilograms per cubic meter. We're looking for the horizontal anchoring force. If we go ahead and think a little bit about what's going on in this problem, we have fluid flowing up and exiting. You can picture that the pipe is going to be wanting to fly towards the left. That must mean that there is some kind of anchoring force, right? There will be a vertical anchoring force, let's call that Fy, and a horizontal anchoring force Fx. Anytime I go ahead and draw forces, I draw a free body diagram, I always have a set of unit vectors that govern my positive direction. And that's one of the key things with problems like these. You want to keep your signs straight. So that's a good thing to do. So we have those anchoring forces, and what we're really looking for is just this horizontal anchoring force. Now, if you ever see a fluids problem where you have some pressures, some speeds, and you're looking for forces, you're going to be using the control volume method, the conservation of momentum. So if we go ahead inside of the handbook, they have it labeled as the impulse momentum principle. What we see is that on page 187 of the reference manual, they say that the sum of the forces is equal to the difference between, these terms are referred to as the momentum flux. You can see that the momentum flux with the 2's, the product of the volumetric flow rate, the density and speed, if they're leaving the control volume, it's a positive sign, versus if they're entering the control volume, it's a negative sign. This is great because it relates speeds and forces. Let's go back to our problem, and let's go ahead and paste this. Okay, so this is our equation here. Now, the next thing that we need to think about is drawing the free body diagram for the system. That's how you always start these kind of problems. So we started off with those anchoring forces. Additionally, there's forces due to these pressure terms. I also see there's a slope triangle here on the bottom left. I always like to work in terms of thetas. So what I could read off from that slope triangle is that adjacent over hypotenuse, cosine of theta, is equal to 5/13, and the sine of theta is equal to 12/13. That's a Pythagorean triple on the bottom, 5, 12, 13. Yeah, I try to use these slope triangles when they're given and not recompute anything, and it helps me save time, and it'll help you do the same. Whenever you draw a control volume around a system, which is this kind of dashed line that I'm drawing here, what it does is it frees the body from its surroundings, and as soon as you cut the body, you're introducing some pressure forces, which is what I'm drawing here, a pressure distribution due to the adjacent water molecules pressing onto this. As soon as you cut the body, these are kind of like internal forces in mechanics of material. You have a pressure force. Its height is P1 with an acting over an area A1. And same thing on the top, right? Everywhere you cut the body and there's fluid entering or exiting, you have a pressure distribution. This is P2A2. Remember that if you have a force, that's just equal to a pressure times an area, which is what we're doing here. We'd also additionally have a weight term due to the weight of that water in the system. Okay, this looks like everything that we need to draw on our free body diagram. Now, all we need to do is plug into the equation and pay attention to some of these sines and cosines. Make sure we get all our signs correct, which is, I think, the hardest part about these problems. Okay, so firstly, let's start with this sum of the forces term. We have a horizontal anchoring force, Fx. Now, we're not going to look at the entire sum of the forces. We're just going to look at the x sum of the forces because we're only interested in this horizontal anchoring force. So just doing the x component of this equation, we have the Fx. We also have this term P1A1. So the entire force is P1A1, but we're not going to see the entire force. If you look at this slope triangle here on the bottom of the screen, we just see the cosine component of it, and it's pointing in the negative I direction, the negative x direction. So what I would write down there is P1A1 cosine of theta, and it's pointing towards the left. So I'm going to put a negative sign there. What about this term here, the P2A2? That's also just pointing towards the left, and there is no slope there. So it's just P2A2 minus. What that's equal to is the change in my momentum flux. Now let's think a little bit about these momentum flux terms. Let's start with the out term. We know the out term as positive sign. At this second point here, we see the speed is pointing towards the right. We have a flow rate. That's Q2, a density, and the speed is pointing towards the right. It's the full speed. That's V2. So this is the correct momentum flux term here. And then we have a minus sign. That minus is due to this minus sign right here. And let's go ahead and write out the inward momentum flux. So that's this term over here. Now again, we're going to have a cosine somewhere, but let's write out that Q1 rho, and then the speed. What's the component of speed pointing in the x direction? That is V1 cosine of theta, and it's also pointing towards the left. it's a negative sign, so that means that we'd have a positive sign here. We had a negative from this, and we additionally had a negative on this term, so this became a positive. Okay, so now that we have all our terms taken care of, we have a bunch of 1s and 2s running around the place. Let's see if we can simplify the problem a little bit, thinking about continuity and thinking about the areas in the problem. Firstly, I know this A1 and A2 terms, as well as these Q terms, the flow rate. Remember that the flow rate is equal to the product of area times speed. All of these terms have an A. So that's something that can be simplified. I would write an A multiplied by P1, and I know the cosine of theta is 5/13. That's from our slope triangle that we looked at earlier. And then plus P2, the A is just, I already factored that out, plus, now Q2. Q2 and Q1 are exactly the same. That's from conservation of mass. We know they're equal to A2 V2, which is equal to A1 V1. Now A2 and A1 are exactly the same. That means V2 and V1 are the same. We didn't use mass flow rate here because we're dealing with the liquid system, and in a liquid system, the density is going to be constant. Instead of looking at rho AV, we just looked at the volumetric flow rate, which is AV. Okay, so let's continue on. If we substitute in here a speed and an area, what we end up getting is that area term we already factored out. We have a rho v squared term for the first term, and then added to the cosine component of a rho v squared term. So we have a rho v squared term, but it's not the full thing, it's the 5/13 component of it, the cosine theta component. If we combine some of these terms here, Fx is equal to my area multiplied by, we can start substituting some of these terms in. Actually, let's combine this term here. We know that 1 rho v squared plus 5/13 rho v squared is 18/13 rho v squared. We also add on 5/13 of P1 and a P2. So this is our full equation here. All we have to do is plug in now. We know that P1 is equal to 200 kPa. P2, that's this term right here, that's equal to 150 kPa plus 18/13. And then we have density, 1,000. Speed, the speed was 10 meters per second squared. I'm going to speed through the rest of this, work through the units, and you can tell me if you got the same answer. You can leave a comment down below. Also, if you haven't yet, please leave a like down below and subscribe. It really helps me out a lot. It's super encouraging and lets me know that you're enjoying the content like this. Let's run through the rest of these units. All right, so what we get here is 4.13 kilonewtons. Let's go ahead and see if we're correct. That's pretty close to this answer on the top, and we are correct here. Let's go ahead and move in to the next problem. In this problem here, we have a spherical water tank, and it's mounted on top of a vertical cylindrical post, and the diameter of that post, that cylindrical post, D sub C, is equal to 3.5 feet. The wind blows at a constant speed of 15 miles per hour perpendicular to the structure. I know what the speed is, 15 miles per hour, assuming uniform flow across the entire assembly. So if we kind of drew how that velocity distribution looks here, draw that a little longer. Kind of a uniform distribution, which is what they told us to assume here, and an air density of that many slugs per cubic foot. Let's go ahead and write that down. The density is 0.0022 0.21 slugs per cubic foot, and a dynamic viscosity, that is variable mu here, is equal to 4.24 times 10 to the minus 7 pound second per foot squared. The moment reaction at the base of the post is most nearly, so we're looking for that moment reaction M. You can see it's a fixed end over here. If we kind of quickly drew what kind of reactions we would expect there, at that fixed end, we'd expect no translation of that fixed end. So of course, we'll have a vertical and a horizontal reaction force, but then there's no angular displacement at the end either. If it's kind of blowing clockwise, we'd expect a counterclockwise moment at the base. So that M is what we're looking for. Additionally, due to that velocity distribution, there'll be kind of a pressure acting on the entire structure. And because it's uniform, there'll be a uniform section on the cylindrical portion, and then there'll be a uniform section on the spherical portion. We would place the drag force that is produced by that uniform pressure distribution at the centroid. So this would be this distance from the base all the way to the centroid of that cylinder. It's 18 minus 8. That means this is 10 feet here. We know that this is 5 feet here. That is this. So that would be the drag force on the cylinder. I'm going to call that F, the cylinder. And additionally, there is a drag force on the sphere. We would place that at the centroid of the sphere. Drag force for the sphere. Okay, and that will be placed at 18 minus 4, 14 feet from the base here, such that we could take a moment about this point at the base so that we can get the counterclockwise moments equal to the clockwise moments. There's only one counterclockwise moment, that's the moment reaction, M, and then there's two clockwise contributions. That is the drag force for the cylinder times 5 plus 14 times the drag force for the sphere. So if we can find the drag force for the cylinder and the one for the sphere, then we would have this problem solved. Now, how do we go about finding the drag force for a cylinder or a sphere? Well, we use the idea of the drag coefficient. And where could we find some more information about the drag force? Let's go ahead and pull up the FE reference manual here. So you can see first mention of the drag force on page 184 of the reference manual. The drag force is just the dimensionless drag coefficient multiplying the dynamic pressure. The dynamic pressure is rho v squared over 2. That is from, that's a concept from the Bernoulli's equation. Also shows up in the energy equation. So we take the drag coefficient, multiply it by the dynamic pressure, and then we multiply it by something called the projected or frontal area, and that's the area that you would see if you're looking from the flow towards that object. So if you can kind of picture the cylindrical object, you're looking, your eyeball is kind of in this orientation. What you would see for a cylinder is a rectangle, and it would have a height h, and its diameter would technically be its width. What about for the sphere? If you're looking from the flow side to that spherical object that we have, then all you would see is a circle with diameter d. So that is kind of the frontal area that we're going to be talking about. And the thing about the drag coefficient is that it's only a function of the Reynolds number. So you can see that they have some mention of things about flat plates here, but we don't have a flat plate. What we have is um, flow over these objects. That's the idea of external flow. And if we head all the way down to the end of the fluid section. You can see there is a chart here for drag coefficients for spheres, disks, and cylinders, and what we have is a sphere and a cylinder. So our plan for this problem is going to be to calculate what the Reynolds number is. Once we know what the Reynolds number is, we'll come in at that Reynolds number and read off what the drag coefficient is. That's going to be the y-axis over here. We're going to take that drag coefficient, multiply it by the dynamic pressure times the frontal area to get the drag force. So the first step in all of that is to find what the Reynolds number is. The Reynolds number, based on the cylinder here, that is just the density of the air multiplied by the speed of that air, rho v d, divided by the absolute or dynamic viscosity. And you could see that in the problem, when they mention the units here, they just put pounds, and that's pretty common, right? We don't always specify whether it's pound force or pound mass, but if you think back to Newton's law of viscosity, shearing stress is equal to mu du dy, and I usually like to think about things I don't know the units for in terms of their kind of fundamental equation, which is this. We know that the shearing stress tau is pound force per, I'm going to put foot squared here, but typically it's pound per inch squared, like a PSI or KSI. I'm going to put foot so we could be more consistent with the units that are given in this problem. And then we have the velocity gradient, that is feet per second divided by feet. So it's just 1/2. So if we kind of solve for the units of mu, what we end up getting is that it is pound force second per foot squared, and that looks very close to the unit that we have given in the problem. So I know that that is going to be a pound force there. Okay, so what I'm going to do is plug in to this cylinder Reynolds number, and I know that it's a pound force, so I can be consistent with my units here. What is my density? It's 0.00221. What is my speed? 15 miles per hour. The diameter of that cylinder, that is 3.5 feet. That was mentioned inside of the problem, as well as the absolute viscosity here, 4.24 times 10 to the minus 7. And let's go ahead and work out these units, right? Because we need to make sure there's no G sub C, no hidden conversion factors in here. So we have the density that's measured in slugs per cubic foot. We have the speed that's measured in miles per hour. We have what the diameter is measured in feet. And lastly, we have what the viscosity is. It's pound force second per foot squared. Okay, so a lot of units here, but we can slowly break it down, and we'll make sure that we have the kind of correct set of units so that everything crosses out, because we understand that the Reynolds number is a dimensionless value. Now, pound force, a slug foot per second squared is a pound force. So you can see that the pound force is going to cancel out the slugs. They're going to cancel out. I have a feet here. That's going to cancel. Okay. A lot of the feet here cancel. So it looks like I'm almost finished. What I need to do is convert that miles per hour to feet per second. So I know that there is 5,280 feet contained in a mile. That's going to get rid of that, and it's going to cancel the last feet on the top. And all that we're kind of left to do is cancel out that final seconds in the denominator. We're going to convert that hour. There's in 1 hour, 3,600 seconds. And now we can finally kind of see that all of our units crossed out. All we had to do was convert the miles per hour to feet per second. So the conversion factor here is 5280 divided by 3600 to get a dimensionless number. Let's go ahead and note down what this is. 401,344, and it is dimensionless. That's an important value. We're going to use that in a chart a little bit later. What about the Reynolds number for the sphere? If we plug in quickly for the Reynolds number for that sphere, we have pretty much all the same terms, but the diameter value is going to change. We have this diameter was for the cylinder. We could plug into that equation again, but if you look at the Reynolds number for the cylinder, it's very similar. It's rho v d sub c divided by mu, all pretty much the same stuff, but that diameter of the cylinder needs to go. So what I'm going to do is multiply by the ratio of the diameter of the sphere to the diameter of the cylinder in order to get my answer here. So what I get here is 917,358. Okay, so now that we have what the Reynolds number for the cylinder and sphere are, we can go back into the FE reference manual. So you can see I went ahead and logged down the Reynolds number for the cylinder and the sphere that we found. So we're going to start off with that sphere. That sphere corresponds to this kind of solid line over here. So we're going to follow that solid line all the way to 9 times 10 to the 5th. That is somewhere around here. And the intersection where it occurs is, around there. All right, so that is for the sphere. Now, what about for the cylinder? We're going to go to 4 times 10 to the 5th. And you can see I kind of dropped off some of those decimal values. These are pretty close to the 4 and 9 values. So in terms of what we're looking for this problem, it's sufficient. Now, if we think about what's going on for the cylinder corresponds to this kind of spaced out dashed line, and looks like it's somewhere around this value here. So let's go ahead and that's 4 times 10 to the 5th. Going to jump over to this line here. Okay, now we just have to interpret what that drag coefficient is. And one thing I forgot to mention was this drag coefficient is very similar to the friction factor from the Moody diagram. So if I go ahead and write down that equation for the kind of head loss, it's F L over D V squared over 2G. And I like drawing these analogies. It helps me kind of remember some of the information better. So you can see just as we multiply a kind of kinetic energy term by a dimensionless parameter, the um, uh, Moody friction factor, pretty similar to what we're doing here, right? Except we're multiplying the kind of kinetic energy version of pressure. Okay, so that was a little bit unrelated. Let's get back into what we're doing here and how to interpret these values on the y-axis. And here's how I like to think about it. If you have a log scale, which this is a log scale here, what you could say is think about the kind of fundamental relationship for a log. We know that this relationship holds true. 10 to the 0 is 1, and we can keep writing this relationship. 10 to the 1 is 10. 10 squared is 100. What you see on the right is a linear interpretation. What you see on the left is a log interpretation. And for me, it's much easier to kind of read these lines in terms of their linear interpretation. So if we go ahead to 1 on the log scale, which is this value right here, that means 0 on the linear scale. If we go to 10 on the log scale, that means 1 on the linear scale. If I go down to this blue line, I'm at approximately 50%. Negative 0.5 on the linear scale, right? Because I'm below the 0 point I'm calling for my linear scale. That means that on the log scale, this point is actually 10 raised to the negative 0.5. And this one, I would call this kind of an eighth of the way from the bottom, or 7/8 away from the top. So this one is kind of 10 raised to the negative 7/8. Okay, just to kind of quickly talk through what we just did. We're looking at these log scale axis, and what we're saying is that the 1 is kind of equivalent to a 0 on the linear scale. So if I write the linear interpretation in this kind of purple color, this is 0 on my linear scale. This is 1 on the log scale. I'm looking at this relationship right here. If I go down to -1 and I kind of read off linearly what I think the points are, I think that this point is around -0.5 and this point is around -7/8 on the linear scale. Now, how do we interpret that via the log scale? We just use the kind of relationship for logs, right? 10 to the 0 is 1. But instead of this being 0, it is -0.5 here. 10 to the -0.5 is what that is in log scale. 10 to the -7/8 is what that is in log scale. So I'm going to use that information to write down what my drag coefficient is. I get around 0.32 there. What about down here? My drag coefficient for the sphere, 10 raised to the -7/8. I get around 0.13. Okay, so does this make sense in terms of the ticks? I know that this is 2 over here, and I'm bounded between at least 0.2 and 0.1, and that's 0.13, so that one makes sense. What about this one? I'm bounded between 2 and 4. This is a reasonable answer here. So let's go ahead and plug these values in to our equation. So you can see over here, I went ahead and logged down what we got for the drag coefficient for the cylinder and sphere. And if we think about what we were looking at for the drag force, it is just the dynamic pressure, rho v squared over 2, multiplied by the frontal area, multiplied by the drag coefficient. If we plug into our moment equation that we found, all we're going to do is substitute in for the drag equation. We know that there is a common term, rho v squared over 2. That is the dynamic pressure, common to both of those terms, but they have unique frontal areas. For the cylinder, they have unique drag coefficients, and their moment arms are different. Same thing for the sphere. All right. So if we talk a little bit more about that frontal area term, which is something that we're going to need to find, the frontal area for the cylinder, it's just what you would see looking from the flow side towards the object. It is just a rectangle for the cylinder. 3.5 feet is the diameter and the height is 10 feet. So we're looking at 35 square feet for the cylinder. And again, if we look from the flow side towards that sphere, we'd see a circle. That is pi times its diameter, which is 8 squared over 4 pi d squared over 4, which is just 16 pi. Let's go ahead and substitute in for that cylinder. We're going to substitute in a value of 35 square feet. The drag coefficient for that cylinder, that is equal to 0.32. For the sphere, we know it's 16 pi was the frontal area for the sphere. The drag coefficient was 0.13. And we kind of understand what the density or the speed is, but we have to make sure that our units are consistent. Let's write down the final relationship here, and we'll do our final unit check here. 0.00221 slugs per cubic foot multiplied by 15 miles per hour squared divided by 2. And if we plug in to our relationship, 35 times 0.32 times 5 plus 16 pi multiplied by 0.13 multiplied by 14. And this is going to be our answer. We just have to make sure that our units are going to work out. The density units, those are in slugs per cubic foot. And of course, we have the miles per hour term, which is squared. We have the frontal area measured in square feet, and we have the moment arm measured in feet. The drag coefficient is dimensionless. You can see that the foot, the cubic feet term cancels. All we need to do is convert the miles per hour to feet per second. We did it above, right? It was just 5,280 divided by 3,600. That is the feet per second to miles per hour conversion, but we're going to square this entire thing such that the miles per hour is going to end up canceling out. We end up with a slug foot squared per second squared. That unit, slug foot per second, is a pound force. Slug foot per second squared, foot per second squared. Okay. And yeah, so we end up with 1 foot here and a pound force here to finally conclude that the unit is foot-pound force. That is the correct unit that we're looking for over here. All we have to do is multiply our answer by 5,280 over 3,600 squared. If we go ahead and plug into this relationship, what we end up getting is that the moments at that base is 78.9 foot-pounds, and that is foot-pound force. It is answer choice A, and sorry if you tried to solve this problem beforehand and didn't see the answer choice on the screen. That's because I ended up changing the answer choices afterwards because I found a mistake in the problem, but should be correct now. Okay, let's go ahead and move on to the next problem. All right, in this problem, we're going to be reviewing the idea of compressible flow. We're going to talk about the definition of Mach number, some of the isentropic flow relationships, and the idea of the converging-diverging nozzle and how we're able to achieve supersonic flow. So let's go ahead and get right into it. It says a converging-diverging nozzle operating under isentropic conditions is shown above. So we know the flow is isentropic. The Mach number at point 1, M1 is 1.3. And the static pressure, and we're going to talk a little bit about what static versus total pressure is. The static pressure at state point 1 is equal to 147.4 kilopascals. Knowing the static pressure at state point 2 is equal to 70 kilopascals, and you could see some of these state points mentioned here, those stations. The Mach number at point 2 is what we're looking for. And you can see we're given a ratio of specific heats. This is known as K. K is equal to 1.4. Okay, so the first thing I'd like to talk about is the definition of Mach number. Mach number is usually denoted as variable ma, and it is just the ratio of your local speed to the local speed of sound. And note that the local speed of sound is a function of temperature. It is the square root of the ratio of specific heats times the specific gas constant multiplied by the absolute temperature. So the Mach number is a function of temperature, and it tells you, um, you know, what your speed is relative to the local speed of sound. So if your Mach number is greater than 1, we call that supersonic flow, since you're greater than the speed of sound. And if your Mach number is less than 1, we call that subsonic. And there's a specific way to achieve supersonic flow, and we do that using a converging-diverging nozzle. If you think about a garden hose and you put your thumb over the end of a garden hose, you're decreasing the area, the exit area of that garden hose. That means you're going to increase the speed, and that is typical for subsonic flows, like the flow of water through a garden hose, right? What we're doing is we're squeezing this initial area. We're initially converging, right? And as we converge, we're increasing the speed of that subsonic flow. So to the left, we have Mach, which is less than 1. And the smallest area is known as the throat. So once we reach the throat, we have two options. We can either have a Mach which is equal to 1, and that is when we can achieve supersonic flow, or we can have a Mach less than 1. And in that case, if the Mach is less than 1 at the throat and we expand the area, we're going to decrease the speed. But in the special case where we have a Mach number equal to 1 at the throat, then something special happens. And for supersonic flows, the relationship between areas and speeds is a little bit different. As you expand the area for a supersonic flow, the flow speed is going to increase. So that's why we have a converging section. That the goal of the converging section, when you're trying to achieve supersonic flow, is to increase the speed such that you have a Mach number equal to 1 at the throat. And at that point, you want to expand the area. And as you expand the area, the supersonic flow is going to increase its speed. The Mach number is going to increase at that point. So the only way to achieve supersonic flow is to get a Mach number equal to 1 at that throat. And if you're anything less, you're going to have subsonic flow throughout the rest of your nozzle. All right, so that's a little bit about the converging diverging nozzle. And how are we going to go ahead and solve this problem? We're going to use some important relationships here, isentropic relationships. And that really will get us into the discussion of the difference between static and total properties. So if we check inside the FE reference manual here, what you can see is this section on compressible flow. It's going to discuss a little bit about the idea of the Mach number. You can see the definition of the Mach number here on the bottom, the ratio of the local speed, V, divided by the local speed of sound, C, and that's a function of the absolute temperature. We have some isentropic flow relationships that relate static properties, and this is from the idea of Bernoulli's equation. We know that if we write down Bernoulli's equation in head form, this first point is called the static head, and if we wrote it in terms of pressures by multiplying this entire term by gamma, then we would have this P1 is known as the static pressure, right? And if we multiply this by gamma, we have a rho V1 squared over 2. We just saw that in our last problem related to external flow. This is the dynamic pressure. The sum of the static plus the dynamic pressure is what we call the total pressure. The total pressure, or we can also call it the stagnation pressure. The total or the stagnation pressure is the sum of the static and dynamic pressure. There's also static and dynamic temperatures, right? It's just a sum of static and dynamic is total. And there's something special about isentropic flow. It's that the total properties remain constant throughout the flow. Like the pressures that we were given, the total pressure remains the same. We don't know what the total pressure is, but if we think about what we know at state point 1, we know the Mach number at state point 1, and we know the static pressure at state point 1. We can use these two things given at state point 1 in order to give us what the total pressure is at state point 1, the stagnation pressure. That is the same thing as the total or stagnation pressure at state point 2. We can use this total or stagnation pressure at state point 2 along with the static pressure that's given at state point 2 to produce the Mach number at state point 2 using this relationship right here. So let's go ahead and see if we can execute on our plan. We're looking at this left-hand side relating the total and static pressure, and the right-hand side which kind of relates them to the Mach number. So that is all about isentropic flow, compressible flow. There's some relationships for area, and then we have shock waves. Across shock waves, we have a big drop in properties and a lot of different changes. And if you have a shock wave problem, you know that across a shock wave, you go from Mach greater than 1, so a supersonic, to a subsonic flow is what happens across a normal shock, and there's some relationships here. You can follow those if you get a normal shock wave problem. Okay, but for our problem, we have this relationship. Let's go ahead and execute on our plan. So we have that the ratio of total to static is equal to 1 plus k minus 1 over 2 multiplied by the Mach number squared, and we take this entire relationship and raise it to the k over k minus 1. If we were to fill in k equal to 1.4 for this relationship here, so we can simplify a little bit, 1.4 minus 1 divided by 2, that gives us 0.2 here. So let's write that down, 0.2. And what about up here? 1.4 divided by 0.4 is going to give us 3.5. So let's fill this in as 3.5. And now we have a little bit of a simpler relationship. We're going to use the initial Mach number that's given. The Mach is state point 1, and the static pressure is state point 1 to produce the total pressure at state point 1. That's the same thing as the total pressure at state point 2. It's just that static pressure at P at state point 1 multiplying 1 plus 0.2 times the Mach number at point 1 squared raised to the 3.5. If we plug in the static pressure at state point 1, that was equal to 147.4 kilopascals. 1 plus 0.2 multiplied by the Mach number at state point 1, that was 1.3 squared raised to the 3.5, 408.408 kilopascals. So now that we know what the stagnation pressure at state point 2 is, we can use that along with the static pressure to find what the Mach number is using this relationship. That's equal to the same thing, 1 plus 0.2 times the Mach number at 0.2 squared raised to the 3.5. Okay, so we're looking for the Mach number at state point 2. That's going to mean that we're going to have to isolate the Mach number. We can raise both sides to the 1 over 3.5, subtract off 1, divide by 0.2, and take a square root to find the Mach number at state point 2. It's the square roots of the static pressure at state point 2, that was around 408.408, divided by the static pressure at state point 2 was given as 70, raised to the 1 over 3.5 minus 1 divided by 0.2. 1.81, that's pretty close to 1.8, so it looks like the answer choice is answer choice C. Okay, let's go ahead and move on to the next problem. In this problem here, we're going to be discussing the idea of pump power and efficiency as well as pump performance. We're going to talk about things like the net positive suction head available and required, as well as the idea of cavitation. So let's get right into the problem. It says a centrifugal pump transports water at a rate of 900 gallons per minute. That is a flow rate equal to 900 GPM. From an underground tank to an elevated tank 30 feet higher, and the system has 12 foot of frictional head loss. So if I kind of draw here, 2 tanks, 1 elevated tank, as well as a kind of lower tank here, we understand that the distance between their water levels is 30 feet, and we additionally have head loss due to friction of 12 feet here. There's a pump between these 2 reservoirs, and we're kind of sucking water from that bottom portion, that bottom tank, transporting it to this upper tank here. 30 feet long and 12 feet of head loss. And at this flow rate, the pump's efficiency, eta, is equal to 68%. The pump performance curve lists the required net positive suction head, the NPSHR, as 15 feet, and PSHR equal to 15 feet. And I'm going to talk about what that is exactly as we move through the problem. It says the water surface in the underground tank is 10 feet below the pump center line. So this distance right here, 10 feet. The suction pipe introduces an additional 3 feet of head loss. So the head loss in this section is 3 feet, that little small section, but the total head loss, right, was 12 feet. So that's just kind of a contribution to the system head loss. The tank is vented to atmosphere and the water is at 25 degrees Celsius. So it's pretty close to a kind of room temperature value, 25 degrees C, or we can call that, yeah, 25 degrees Celsius is fine. Okay. Which of the following is closest to the input power required by the pump? So we're looking for the pump power and will cavitation occur? So we're going to talk about the idea of cavitation, but first, let's focus on the idea of pump power and how we can find that pump power. So there's an equation in the FE reference manual which discusses the idea of pump power, and that is on page 192 of the reference manual. You could see that pump power is just the product of the volumetric flow rate, the specific weight, the head, and then the efficiency. And they have the efficiency broken up into a pump and a motor, but we're just given one kind of bulk efficiency. So that's what we're going to apply. We're going to use this equation. The specific weight of water, it's 9810 newtons per cubic meter, or in the English system, it's 62.4 pound force per cubic foot. And I also want to make a point here. The density of water in the English system is also 62.4 pound mass per cubic foot. So you can see some people get confused because these values are exactly the same, but it's different in the metric system, right? We have a density of 1,000 kilograms per cubic meter and a specific weight equal to 9810 newtons per cubic meter. And the reason that these two values are the same is just because of that, the definition of pound force and pound mass, right? Remember that the definition is in 1 pound force. A pound force is defined as the amount of force necessary to accelerate 1 pound mass at a rate of 32.2 feet per second squared. So if you plug this kind of conversion factor into the definition of the specific weight for the English system, density times gravity, what is the density? It's 62.4 pound mass per cubic foot. What is gravity? It's 32.2 feet per second squared. And notes, you have a pound mass foot per second squared. That is almost what's required to go from pound mass to pound force, but we're missing a factor, that 32.2. So a pound force is 32.2 pound mass feet per second squared. The pound mass will cancel. The pound force is there. The second squared cancels. The foot cancels. All we're left is pound force per cubic foot. And you can see this critical cross out right here. The gravity term cancels. So that's why the density and the specific weight have exactly the same magnitude. So that's a little bit confusing. And you could see also that I have memorized the specific weight and the density of water in the English system, just like I have it memorized for the metric system. Right? I know that 1,000 kilograms per cubic meter is the density of water. 62.4 pound mass per cubic foot is that for the English system. So I recommend you memorize these quantities. Okay. If you didn't want to memorize them though, there is a table on the bottom of this section that you can use to find what the density is. And for liquids, the density is going to stay pretty much constant throughout its temperature. It's going to vary a little bit, but not enough to impact the calculation by too much. So what do we have here? We know that the pump power is going to be equal to the specific weight. We have a flow rate and a head term, and we're going to divide that by the efficiency. Okay, so now that we have the pump power equation down, all we need to think about is what kind of head does that pump have to overcome? Now, we could think about it more formally in terms of the energy equation, but if you think about it intuitively, The pump simply has to overcome the entire head due to elevation. That's the 30 feet difference between the two water levels, as well as it has to overcome the frictional effects. That is the 12 feet of friction loss that occurs throughout the length of the pipe. So the total head it has to overcome is this 42 feet. That's the head we would plug in. If we think about it in terms of the energy equation, P1 over gamma plus V1 squared over 2G plus Z1 plus the pump head is equal to P2 over gamma plus V2 squared over 2G plus Z2 plus any head loss due to friction. At the free surface of both of these tanks, it's atmospheric because they're vented. There is zero speed at these kind of large surfaces here on the top because we're thinking that the tank is much larger than the water level. The tank is large, so the water level will rise or drop slowly. So that's why the speeds at point 1 and point 2 are going to be listed as 0. We know that the elevation at point 1, if we take it as our datum, is going to be 0, such that the pump head is just the sum of the elevation of point 2, that's the 30 feet, plus the frictional head loss was given as 12 feet. So that's kind of formally where that comes from. Okay, if we go ahead and plug that into our pump power equation, we have our specific weight, 62.4. Our flow rate was 900 gallons per minute. Our combined head was 42. And our efficiency is 0.68. And if we think about some of the units here, what we see is that the specific weight is pound force per cubic foot. The volumetric flow rate is gallons per minute. The head is measured in feet. We know we're definitely going to have to convert that gallons per minute to feet per second. So how many gallons are in a cubic foot? There is 7.49 gallons contained in a cubic foot. So that's going to cross out. And we know that in 1 minute, there is 60 seconds. So the minutes are going to cross out. The cubic feet are going to cross out, and we're left with foot and pound force. And you could see that some of our power options here are measured in horsepower. There is 550 foot-pounds per second contained in a single horsepower. So that is an important one. 550 foot-pound force per minute contained in a horsepower. Sorry, foot-pound force per second contained in a horsepower. Okay, so you can see that the second here in the denominator of the denominator and the second here in just the numerator's denominator is going to cancel. We can cancel out the foot-pound force here, and we're left with this final unit of horsepower. And the kind of overall conversion is 1 over 7.49 times 550 times 60. What we end up getting is that the pump power is equal to approximately 14.03 horsepower. So that is pretty close to, I know that it is at least options A or B. And now we have to discuss the idea of cavitation, and that's where the idea of net positive suction head comes into play. So let's talk about the idea of cavitation. So when you have a pump and you're pulling fluid from a reservoir that lays below the pump, what happens is as you travel up this tube, the pressure is decreasing. Now, if you decrease the pressure below a certain point, you know that boiling of the fluid can occur, right? You can have a phase change. If you think about if you go up into the mountains, right, and try to boil water, you know that it's going to boil at a lower temperature, and that's because the pressure is lower as you increase your elevation. If you decrease the pressure by a lot, water can boil at a temperature like 25 degrees Celsius. And that will happen if you drop below the vapor pressure. Cavitation is what's going to occur when at the entrance of the pump, you you go from liquid to vapor. So you have this kind of liquid vapor mixture that's entering your pump, and the pump, its job is to increase the pressure of the fluid. So as you increase the pressure of the fluid, which is liquid and vapor at this point, um, those vapor bubbles are going to begin to collapse, and they end up corroding the impeller inside of the pump, and it makes a loud noise and it causes a drop in pump efficiency. So we don't like cavitation. But that's the idea of cavitation. Essentially, the pressure drops below the vapor pressure at the entrance of the pump, and you have a liquid vapor mixture that enters the pump. Those vapor bubbles, they end up collapsing in the pump since the pressure increases enough to turn that vapor back into a liquid, and that causes corrosion of the impeller. That's the idea of cavitation. And how do we ensure that we have margin to the vapor pressure? That is really the idea of the net positive suction head available. We compare the net positive suction head available to the net positive suction head required. Positive suction head required. And we ensure that this relationship is true. And then we know for sure that cavitation will not occur. We know what the net positive suction head required is. That was given as 15 feet in the problem statement right here. And the net positive suction head available, we need to take into account things like the vapor pressure. We need to take into account the amount that this pump is, the water level is below the pump center line. We need to take into account what the atmospheric pressure is. So there's an equation for that inside of the FE reference manual. Let's go ahead and check it out. All right, so you can see here that equation for net positive suction head available, and we're going to be plugging into the head form. That's because our net positive suction head required, which we're going to be comparing this to, is already measured in feet. So we're going to have our net positive suction head available measured in feet as well. Okay, all we have to do is identify some of these terms and make sure that they're all consistently in feet of water column. Now, the atmospheric pressure in feet of water column, how do we convert from pressure to feet of water column? That's just using the hydrostatic pressure equation. You can see that how we convert from head, if we're given a pressure like atmospheric pressure and we want to know what it is in head, we just take that pressure and divide by the specific weight of water. So let's say we have what the atmospheric pressure of water is. And we knew what the vapor pressure, another word for the vapor pressure is the saturation pressure, which you can find inside of the steam tables in the thermodynamics section. So those two terms are things that we're going to have to convert from pressures to head. And let's look at the static suction head of the liquid. It says that this is the height of the surface of the liquid above the center line of the pump, while our surface of the liquid is not above, it's below. So it wouldn't be a plus 10. This term would actually be a minus 10. And then we know what our frictional loss is. That was 3 feet, and that is this term right here that I enclosed. Okay, so now that we have pretty much all the terms identified, I'm going to group together the head term for the atmosphere. So that I'm going to call the pressure of the atmosphere. And I'm going to subtract off the vapor pressure or the saturation pressure divided by gamma. So I've taken into account already this term as well as this term. And now I'm going to put together the other two terms. Remember, we are 10 feet below the center line of the pump. So that's a minus 10 contribution. And we are a minus 3 contribution since we have 3 feet of head loss inside of that suction side, just the lower side of that pipe. So this quantity is going to be equal to the net positive suction head available, and our vapor pressure or saturation pressure is just the saturation pressure at 25 degrees Celsius, which was mentioned in the problem to be the temperature of the water, which is located right here, 25 degrees C. Okay, let's head to the thermodynamic section. What you're going to find is that inside of that thermodynamic section, there is no Fahrenheit table, right? And that's why I had to give the temperature in Celsius. So I gave the temperature in Celsius so that you can go to the thermodynamics section and look up at 25 degrees Celsius. What is the associated saturation pressure? You can see I have it circled here. It's 3.169 kilopascals. So that is the associated saturation or vapor pressure at 25 degrees Celsius. And we know what the atmospheric pressure is in the metric system. It's 101.3 kilopascals minus 3.169 kilopascals divided by the specific weight of water in the metric system, which is 9810. And if we work out some of these units here, we have kilopascals, or really, and then the specific weight of water is Newton per cubic meter. We don't want kilopascals, we want pascals in the numerator. So we're going to multiply our numerator by 10 to the third to turn this kilopascals into a pascal. Now that we have a Newton per meter squared in the numerator, which is what pascals is, we can go ahead and cancel out most of these units. And we just have meters, but we don't want meters. Everything else is measured in feet of water column. And this is a good opportunity for me to show you guys how to go from meters to feet. If we go to the on the top of the FE reference manual here in the units and conversion factors, in order to go from meters to feet, this is on page 3 of the reference manual, all you have to do is take that meter value and multiply by 3.281 to get feet. So let's put down our conversion factor to go from meters to feet, which was 3.281. Finally, we get a value of 32.82 feet of water column. If I go ahead and subtract off 10 and then 3, or subtract off 13 from my 32.82, what I end up getting is that my net positive suction head available is 19.82 feet of water column. And that net positive suction head available, if we compare it to the 15 feet for the requirements, we know that or what's available is greater than what's required. That means that this check is true. Because that check is true, no cavitation will occur. That is answer choice D. Let's go ahead and move on to the next problem. In this problem here, I'm going to be discussing the idea of dimensional analysis and similitude, and we're going to go over the Buckingham pi theorem. I'm going to tell you guys why it's important and why I chose to go through that problem as opposed to something about fans, pumps, and compressors. This is really the idea of scaling, and this is the most fundamental thing in this section. So we're looking at the Buckingham pi theorem, and it's all about dimensions. So I'm going to be writing down the dimensions of each of these parameters that are mentioned. It says the speed of ocean waves, and it is variable c. Speed is meters per second here. Of ocean waves in deep water is believed to depend on gravitational acceleration, g, that's meter per second squared. Water density, rho, that is kilograms per cubic meter. Wavelength, lambda, that has units of length, like a meter. And water depth, h, again, another meter term. Using the Buckingham pi theorem, one dimensionless parameter has already been found and is shown above. That is this combination of terms here. Which of the following represents the second dimensionless pi parameter? And you could see the second dimensionless pi parameter has this form with these kind of unknown exponents here. It is water depth raised to some power, density raised to some power, so on and so forth. And our goal is to determine those coefficients and see if we can determine what is that pi parameter, a dimensionless number that will be able to characterize this situation. Now you can see that the form of the second pi parameter doesn't include this c, right? It doesn't include the speed of the ocean waves. That's because after you find one pi parameter, you have to eliminate it from your set of variables that you use to describe the second pi parameter. So the speed of the ocean waves was eliminated and the form of the second pi parameter is given here. And it makes sense. All of the choices don't include that c parameter. So I just wanted to clarify that. Let's go ahead and continue. Before we get into solving this problem, I'm going to talk a little bit about the idea of the Buckingham pi theorem and why it's important. So when we're collecting test data and we're trying to characterize a certain situation or a certain phenomena, there is um, there is a way to be able to simplify your analysis and just reduce all of your terms into a few important dimensionless numbers. And that's where a lot of these dimensionless numbers that we use in fluids come from, right? If you think about the idea of the Reynolds number or the Moody chart, we have a dimensionless kind of axis here where the y-axis is the friction factor, the x-axis is the Reynolds number. There are different lines over here of relative roughness, right? All of these terms are dimensionless and they're fully able to characterize for any pipe material, speed, diameter, viscosity, flow rate. It's not 100 different charts. It's a single chart put on one piece of paper. And that is the application. That's the power of the Buckingham pi theorem. If we think about another example, looking at something that we just did in this video, looking at the drag force versus the Reynolds number, right? A single chart will tell you all for a bunch of different objects, a bunch of different shapes. It'll give you the drag coefficient, right? There's not one for water, for air. It's all characterized onto one chart. Now, in this problem, we're going to be looking for that pi parameter. I'm going to talk you through the different steps that you need to use in order to find a pi parameter. The first thing is determining um, the number of fundamental units that you have in the problem, dealing with mass, length, and time. So your option is 0, 1, 2, or 3. I can see we have a mass, kilograms, we have a length, meters, and we have time as well, seconds squared. So we have 3 fundamental units in the problem, and the total things in the problem that exist, we have 1, 2, 3, 4, 5 variables. If I'm looking for the number of pi parameters, I just take my number of variables and subtract off my number of fundamental units. So this problem is characterized by 2 pi parameters. They already found 1 pi parameter. That is a grouping of terms over there. And our goal is to find the second pi parameter. Now, how are we going to find that pi parameter? We know that that second pi parameter is going to take the following form: a depth raised to a power A, a density raised to a power B, gravity raised to a power C, and wavelength raised to a power D. And what we want is the unit to be nothing. We want the unit to be dimensionless here. So if we fill in some of the dimensions here for height or for depth here, we want to fill in meters. For density, we have kilograms per cubic meter. This one is raised to the A. This one is raised to the B. Gravity, which is meter per second squared, is raised to the C. And lambda, or wavelength, is raised to the D. And what we're going to do is make sure that this is equal to a dimensionless value, which means we have no meters, no seconds, and no kilograms. Those will all be raised to the 0 power to produce a constant or a dimensionless value. Now, how are we going to do this? We can just combine the exponents, right? You can see that mass, if we look at all the m's here, we have an a in the numerator. We have a minus 3b, that is from this term right here. We have a plus c and a plus d. So that is what my mass unit is. What about for my kilogram units? I'm seeing a b here, and that's all we have for b. That's all we have for kilograms. And what about for seconds? I'm seeing a negative 2c. And that looks like all we have for seconds. And I know that this must be equal to m to the 0, kilograms to the 0, seconds to the 0. From here, we see that negative 2c must be equal to 0. That means that c is equal to 0. This parameter doesn't exist. There's no time inside of our dimensionless parameter, as well as b. You can see that the kilograms, b is equal to 0, looking at the kilogram equation. This is also going to be 0. So we just have some combination of, some combination of A and D that we're going to be looking at. We know that B is 0. We also know that C is 0. So what this equation is telling me is that m raised to the A plus D must be equal to m to the 0, or A is equal to negative D. Now we know that our pi parameter has the following form. The a exponent is equal to negative d exponent. Let's call that constant. Let's call it uppercase A. Okay, what about B and C? Those are both equal to 0. If we look at the form of our pi parameter up here, what that means is I know pi 2 is the following. B and C are both raised to the 0th power, and A is equal to negative d, or what I have is h over lambda raised to some power. Now I could set that A equal to 1, 2, 3, and the answer would be correct. But if you look at the choices on the left-hand side, you can see that we have this answer choice B as our pi 2 parameter. And I marked this question as easy. You could see the tag here, because what we could have done is check some of these choices over here. Check these choices over here, and we can quickly see by inspection that answer choice B is a length over a length. It's a dimensionless term, so that must be the dimensionless pi parameter. But I wanted to go through this procedure so that it's clear on how you perform the Buckingham pi theorem and how you use it to find the important dimensionless parameters here. So if I was going to put this on the axis, I would put pi 1 is some function of pi 2. Just like the friction factor is some function of the Reynolds number, or the drag coefficient is some function of the Reynolds number. Okay. Now, if we check inside of the reference manual where some of this information is, we can go ahead and check out in the dimensional analysis section. It talks about the Buckingham pi theorem here. It talks about the number of independent dimensionless groups that may be employed to describe a phenomena. Mass, length, and time, that's the 3 that we counted before. How many kilograms, how many meters, how many seconds, and then how many variables that we have. We had 5 in our case. We took their difference. We found that 2 variables, 2 pi parameters, could fully define the entire situation. Okay, so that was the idea of the Buckingham pi theorem. I hope it was helpful. Let's go ahead and move on. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam, so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know, what are my top 3 subjects? What are my bottom 3 subjects? Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $9.99. Let's get back into the video. If you made it this far in the video, I just want to say thank you. And if you found this video useful, I would really appreciate if you leave a like and subscribe if you're not already subscribed. Additionally, if you could share this video with anyone you think you would find it useful, that would be amazing. I'm a small channel and I'm always trying to grow and improve. So if you have any comments on the next review you want to see, or have any questions about the content we covered in this video, or generally about the FE Mechanical exam, don't hesitate to leave a comment, or reach out to me however you can. Thank you for watching. I hope to see you in the next one. Goodbye.